All right, cool. Hi, thanks everyone for being here. My name is Raul Kripalani. I'm going to talk more about technical details on the IPC stack. And as you've heard from Juan, Parth, and you'll hear from everybody else, the IPC is actually a product that is coming out of R&D into productization in these stages. So I'm hoping that with this talk, as we go and continue building the stack and building on the vision that Juan, Parth, and others have communicated, and I'll continue to touch on. I'm hoping that with this talk, I'll convince you on the technical merits and also like the technical underpinnings of the IPC stack, so that you'll follow all the progress with us and continue adopting new features as they come out straight up out of the pipeline. So as you've heard. IPC is a scalability framework that unlocks planetary level performance for Web3 while delivering frictionless developer experiences to power a new generation of apps that breaks Web 2 limits. I think we're coming to this space with kind of a fresh perspective on how the current ecosystem and the current trends are failing to meet the demands in terms of scale, in terms of developer experience, and so on. And we're coming to it with a very fresh perspective, inspired by by what has worked in terms of architecture for the internet and what has gotten us to this point. So just to give you a sense of, like, as I was mapping what the Web3 space looks like today from the perspective of a developer coming to it and just simply scratching the surface of Web3, today, if I were a Web2 dev, I would be coming in and I would be very curious about Web3 and I'd be wanting to adopt decentralized tech. And I would, one thing that we don't really talk about a lot is maybe I already have an existing app and I might want to start progressively adopting some of the Web3 primitives like privacy, like decentralizing specific parts of the logic of my app, but not the entire app as a whole. And we're basically today, it's a 0-1. You either are entirely Web3 and you port your idea or build your idea on an entire stack where you look at the concepts and none of these actually translate at all to Web 2. So you're coming to this world and you're confronted with this deluge of foreign terms and you don't know where to start, right? So of course we have kind of a cold start problem in Web 3, but then users and developers are generally accustomed to Web 2 tech, things like cloud architectures and AWS and Azure and so on, and they have great libraries and frameworks like Vercel and Netlify and things that they can very quickly start develop apps with. So the question is, why would they even look at Web3 if it's not kind of for the principles, if Web3 is not really today meeting the scalability requirements of that they're going to be having, right? So so yeah, and this is compounded by the fact that new concepts continue to appear practically every day, different new layers, and the ecosystem itself is as well very fragmented. So there's new concepts appearing on different parts of the ecosystem every day, and it's really hard to keep up with, right? So IPC was born originally as hierarchical consensus, and I personally think of it as an architectural fabric that underpins much of what we're building here in terms of an architectural fabric that allows us to scale blockchains and distribute workloads and programs into infinitely scalable tree topologies that are deeply customizable, where every single node is entirely deeply customizable and hyper-tuned to the needs of the specific app, the specific service, or the specific thing that's actually running there. Marco is coming after me, and he'll tell you a little bit more about how IPC compares to other solutions out there. But one point that I wanted to mention as well is that IPC inherits security features from an IPC subnet, inherits security features from its parent, but also IPC enables this substrate of cross-communication between subnets in a seamless way, in a seamless way. And it also eliminates the need for kind of when you look at different solutions out there, and you look at how the different nodes and the different networks and those solutions would speak to each other, it usually involves bridges, right? And it involves things like oracles and so on, and those are inherently, in many cases, insecure and have been subject to attacks and so on. So IPC provides all of that substrate for intercommunication in the framework itself. Now, the key concept in IPC and the key unit of abstraction is the subnet. So the subnet is this key concept where we aim to unify and bridge the chasm between Web 2 and Web 3. And subnets are the thing that actually give us horizontal and vertical scaling. I'll talk more about this in a second, but a very important variant of the scaling is the fact that subnets can be ephemeral and can have dynamic life cycles. So it's very easy to spawn off a subnet and then destroy that subnet, and we'll see in a second why you want to do that. Subnets can be grouped in topologies following arbitrary heuristics. The protocol does not care about how that happens. You can set your membership rules, and then validators on a subnet can only join if they satisfy those membership rules. As I said, the framework provides seamless communication and value transfer, and there's the ability to locally hyper-specialize subnets, provides partition tolerance and isolation between subnets as well. So what can a subnet host? Like, what would you think a subnet can contain inside it? A subnet can be an application, can be an entire application in itself. It can be a whole vertical or a domain of applications. So you can imagine there are developers and people out there that create subnets that have very specialized fast consensus like the one that Juan was talking about, and these could be multi-tenant subnets, right? So they're offered as a service, and there could be new businesses emerging on top of IPC by developers that build and fine-tune these consensus and potentially even take them from R&D and provide really high quality, even like customized syscalls on the FEM, I'll talk more about this, that are specifically specialized for game development, for example, right? A subnet can also represent a region. It could represent all of EMEA. And when you marry this with membership rules that I just talked about, it becomes very clear how a particular subnet can decide which validators are able to join it and which it will reject, depending on an arbitrary rule, which could be geographical location. It could be the autonomous system that a particular node is running in. It could be a BGP route. It could be an IP, their IP address. It could be a latency probe. It could be anything here, right? A subnet, I find this super interesting. A subnet can be a service as well. So you can imagine having a database where currently is like really hard to think about a database in Web3, right? But imagine having a database that has where the logic of that database and kind of like the framework itself and the low-level primitives are running on a subnet that provides a set of syscalls that allow super fast access to I/O, to local I/O on a disk, and then a number of primitives to kind of like guarantee proofs, guarantee some properties about the data or whatever, and like an entire, you can imagine a subnet is like a database, and because subnets can communicate with one another, you can imagine that an app is talking to a database, and boom, you've got a more traditional Web 2 like architecture, where each of those is specialized in its own thing, and the framework is providing for the communication between those subnets, right? You can also have general purpose subnets for scaling, and a whole data center could be a subnet, for example. So this is super interesting where, when you start getting into trust domains as well, you can imagine a subnet being a grouping of machines that are in a well-known trusted domain and trust each other. And they don't need to arrive to consensus at every single transaction or every single unit of time, but they might only need to arrive to consensus when they need to demonstrate that they behave correctly to the parent, right? So you remove, if you add the layer of the trust domain here, then you get to a point where, similar to what Juan was saying, which is, most of our algorithms today are geared for global participation. But what about if we look at what local participation in a network would look like and really hyper-optimize for that? And another point that I wanted to bring home as well is that starting a subnet in IPC creating a subnet in IPC is only the start. Because that subnet then can spawn new subnets. And we'll see that in a second, and it can give rise to an entire new topology, right? So putting all this together, imagine we have a tree, number of subnets here and there, and these subnets are grouped in, can serve different purposes. You can have app-specific subnets, geographical regions, and infrastructure services. When a game, for example, starts becoming very popular, it can decide to spawn a new topology within it to cater for users within different geographies, such that the latencies that those users will perceive is way lower than if they were participating in a global network, right? So this is how we enable that like capillarity at that level. Now, I just wanted to give you a touch on a few of the mechanics of what happens when you create a subnet, right? How does this process actually work? And a little bit on the lifetime and the life cycle of subnets. So first of all, when you create to create a subnet, you would pick a parent, right? And this is the place where you're going to anchor that particular subnet. The first step is to create that subnet, and this creates a definition of that subnet, and you specify a configuration. So you say this subnet is going to have a minimum of X validators, and each validator is required to deposit this much collateral, right? Now, at that point, that subnet exists, or it's defined, and validators start joining that subnet. And at one point, when the minimum criteria are met, the subnet activates, and that is the point where validators can start running the infra to start producing their first blocks. And then as they're producing transactions, validators are continuously checkpointing on the parent, and while they checkpoint, they publish messages that have been originated at that subnet or have been received from children of that subnet. They publish those messages to the top, to the parent, and then there's also a reverse process, which is the top-down process here. So yeah, and actors and subnets can communicate via cross-net messages using these things. Cool, so two key actors that make this happen at the low level are the gateway actor and the subnet actor. So these two work in concert to basically govern the life cycle of subnets, map out the subnets, understand which subnets, or create a registry of those subnets to serve as mailbox for cross messages. So a gateway actor is the subnet registry. It is deployed at every chain that has IPC capabilities, right? So this is deployed in Filecoin calibration, and that is how Mycelium was created, which Alfonso will talk more about in a few minutes. So a gateway actor acts as a registry. It is also a factory for new subnets, and it is also a mailbox for cross-net messages. And then there is a subnet actor, which is the one that is responsible for controlling things like the state of the subnet, the checkpoints, managing its validators, its stake, enforcing slashing soon, and it also dispenses rewards. So if you want to, these actors, by the way, are written in Solidity. So in theory, IPC can be deployed to any EVM-compatible network. We are focusing on Filecoin, but it could be taken to other EVM-compatible networks. And that's the repo in case you're interested in that. Now, one thing that has been mentioned many times is the hyper-customizability of IPC subnets. So I just wanted to touch on this briefly. It's a big slide, so it might not be that brief. But so just wanted to, this is a key aspect. So we've talked about kind of like the tree layout and the microarchitecture, right? And like how subnets communicate with one another and how they relate to one another. But each subnet can be a world of its own, essentially. The IPC protocol does not care exactly about the details within that subnet, as long as the subnet can prove a certain invariance to the parent, and it can communicate with the rest of the tree, right? So things that leveraging a lot of the work that has happened in FEM and other projects over time, you can some ways in which you can hyper customize a subnet are you can deploy high performance logic as WASM actors, and this logic can be written in any programming language that supports WASM. So we're now instantly expanding the set of remember when I talked about the Web3 developer experience, the Web2 is coming into Web3, and like having to learn one of the things that I have to do is like practically have to learn an entire new programming languages, right? Programming language, which also has its dark corners, right? That is Solidity. So imagine devs coming in and being able to just use their know-how in their existing programming languages. As long as they compile to WASM, they'll be able to deploy that code on a customized subnet. You can also restrict user program deployments. So imagine creating, we think about like in general, the space thinks about side chains and and rollups and so on as kind of like general purpose subnets where anybody can come in and deploy programs, right? But if you're creating an application using subnets, maybe you want to be the one that controls the logic that is running in that subnet, and you don't want to let anybody else deploy any logic, right? Because it's super customized for a specific purpose, right? So that's something that you can do. You can also escape to native land via custom syscalls. So if you're familiar with the architecture of the FVM, you will know that one of the key elements there is the kernel abstraction and the way that programs running on the FVM can call out to native features. So you can just add your own syscalls. And for example, I think we'll be hearing from Fluence later today on how they plan to do this with a particular randomness library that they're using that's called RandomX. And this code runs on native, so it's very like you can use it for high performance primitives as well. You can also use your native coin and even create your crypto econ within your subnet. You can also bring your FEM runtime, and instead of like in general, the thing here is instead of programs, instead of smart contracts, start thinking about units of computation that are simply on chain, right? These are functions. These could be workloads. This could be jobs. It could be anything. Anything can run within those environments. And one very important aspect is consensus, right? So if we marry everything together and then consensus becomes customizable as well, you can pick your consensus algorithm based on the trade-offs that you want to make at that particular point in the tree. And even the location of validators and the members that are part of that subnet, right? So for example, in the case that I mentioned, a data center, you might not actually need full like Byzantine consensus algorithms at a data center level. You might be okay with some reactive or lazy consensus algorithm that just proves particular invariance at whenever a checkpoint needs to be declared. And in the future, we'll also be providing state storage integration, custom account types, gas schedules, atomic upgrades, and more. So now just touching very briefly on some of the scaling patterns here. Usually the space thinks about horizontal scaling and vertical scaling. We're kind of like using those terms, but in different ways, and I'll explain why. So horizontal scaling is the ability to start new subnets at the sibling level. And this usually do that because you want to scale throughputs, the throughput and resources of the logic that's running at that particular level, or you want to shard activity by some partitioning criteria, right? Now, what's important when you do this is like the application needs to be aware of that partitioning key, right? Or that sharding key, and like likely the parent will need to be aware of that as well. You want to maybe, there comes one point where you have a number of validators running in a particular subnet, and it is consensus is becoming very inefficient because that subnet allowed validators from anywhere in the world to join, and at one point you realize and you want to splinter that subnet to group those validators by region, for example. That would be another case where you create a subnet at a sibling level, and you can also enforce isolation domains, right? Now, in terms of vertical scaling, we're kind of like squatting this term. It means something different in computing. Vertical scaling is adding resources like CPUs and memory and disks to an existing machine to scale its throughput. We're not using it that way here. For us, vertical scaling, we mean creating a new subtopology under an existing node in the tree. And you'll probably want to use this to farm off, for example, a specific class of transactions or activity to a dependent subnet that depends on that point on the tree. So it's a child subnet, and it honors the security characteristics or reports on security to the parent. You can hyper-specialize a portion of the tree. You can organize activity by regions, latency, or other criteria, or even nest a service within a topology entirely, right? So now putting all of this together, adding the fact here that IPC subnets are actually can be started and can be controlled, the life cycle can be controlled programmatically. This creates the environment for logic on chain to have some condition that determines that a particular subnet needs to be created at a particular point in time. with some set of properties and some set of attributes, and this can happen programmatically, which means that, boom, a subnet, there's no user intervention in creating a new subnet. Usually when you look at other scaling platforms and so on, you will there's manual work involved in creating a site and creating a chain and creating a rollup or whatever. In IPC, a rollup can, a subnet can just decide to exist at a particular point in time, right? And why would we want that? This is a key element because this, if you think of it, if you squint at it, it allows you to, it gives the whole stack elastic capabilities, right? Because there's one condition, which could be a throughput limitation, right? That gives rise to more capacity added to the whole topology, right? And that is very similar to, in Web 2, what elastic compute is, right? But also, you could potentially use this property or this feature to run things that are limited in time by nature. So for example, game sessions, compute jobs, ML training workloads, where the validators or the participants congregate in a particular subnet to run a job, and then that subnet dissolves, right? Or request processing, transactions, and stuff like that. So in this diagram, you see kind of a few of the bottom nodes being turned into ephemeral subnets, where you have users or clients of those subnets interacting only with those subnets. Now, a few more things. Flexible topologies. I am running out of time, so I'll be quick. Subnets can filter membership by a number of criteria. That could be geographical location, internet location, autonomous systems, latencies across members, some proof of work, or even some ZK proof, right? So maybe the program has some, the application has some logic that says to be able to join and validate and participate and run this subnet, you need to present a ZK proof that was obtained off band or something like that, right? So of course, this is kind of our vision. I'm mixing a lot of vision and current implementation, so bear with me. I really want to I said at the top of the talk that I want to convince you of why you should be interested in IPC as it continues to develop. So this is something that we're very interested in, and also I think it's going to be key to enable kind of all these flexible topologies that we've been talking about. And our goal here is to kind of build a toolbox. This is already possible today. You can customize some of the actors today, where you could potentially add filtering rules at some levels, but in the future we aim to provide a toolbox of membership rules here. Now, just touching on some technical details on top-down messages and bottom-up messages. So when a child receives a message, this is, as I said, we said that subnets can communicate with one another, and this happens over the tree. So a parent can send a message to a child can send a message to a parent, and any subnet can communicate with one another following the tree layout. So how these, when you decompose this into two actions, the whole message flow happens through top-down and bottoms-up interactions, right? So just touching very briefly on this, the parent gateway for top-down messages, the parent gateway acts as a mailbox, and validators pull messages from that mailbox together with the latest observed parent finality, and they feed those messages into the local execution. They inject those messages into the local subnet, and at the block validation level, other validators only proceed if the view of the parent that they see is consistent with the injected block. On the other hand, we also have bottom-up messages. So subnets and checkpointing. So subnets periodically generate checkpoints, and the period is actually defined at subnet creation time. And at these checkpoints, the subnet is informing of the current state. It is informing of the circulating supply and values exiting the subnet and a bunch of other things that define the kind of the context of that subnet. And they also, with that, forward any messages that have been produced locally or have been produced by children subnets, right? So now with these two primitives, there is the circuitry to make messages flow across the tree. Now, just I'm almost done. So I just wanted to touch very quickly on partition tolerance. We've talked about this several times. So if the local, I think the key element here is that if the local consensus choice allows it and the IPC app supports it, remember that consensus is something that's can be customized. So if you build a consensus algorithm that is aware of partitions and is able to let that application or that subnet continue operating despite being disconnected from its parents or from its children, right? So it's kind of like isolated and it continues operating and it's able to detect when this happens and it's able to keep validators and make this a known fact in the network that this has happened, that everybody agrees that the circumstances happen. It can switch modes into a different mode. You can potentially use CRDTs and other primitives there to later reconcile the state of the parent of the partition subnet with the parent, but also even inside the subnet there could be nodes that simply are gone and they could be operating internally with some CRDT primitives and reconciling the state and when they come back online, right? And I think it's super interesting to think about this also from the perspective of libp2p. When you look at the entire stack that IPC is built on, right? libp2p has the primitives in there to enable offline transports, and there are several groups that are implementing and experimenting with offline transports. So when you marry everything together, you could have an app that uses libp2p, that uses offline transports, that selectively decides at a particular point in time to go offline and continue operating with its peers in its vicinity, and then when it comes back online, it reports the current state and it potentially even merges that state on the parent. Cool. So we've talked a lot about developer experience and how important developer experience is for us. I introduced that massive hairball of Web3 concepts that Web2 devs see as soon as they scratch the surface of Web3. And this is really what we're shooting for, right? We're shooting for the simplicity of cloud deployments. We've talked about elastic compute, programs, specialization, and a bunch of key concepts there that developers just take for granted in Web2. And we're really inspired by the developer experience that they see as soon as you create an app, deploy it, and literally today with the tools that exist, it literally takes a few minutes, right? And it does not require very specialized or expert knowledge because the Web3 space is kind of exposing its wires, right, to devs and forcing them to figure everything out. Cool, so a few things to be excited about that will be upcoming, and when I say upcoming, it's upcoming, right? Will be roadmap not defined yet, but things like, for example, content address state and storage integration. We think we have we think that Web3 apps are not efficiently able to store and access data, and having IPC deployed on Filecoin being a decentralized storage layer, it seems like there's a ton of synergy to finally make it possible for programs running on chain to read and write data that is stored on Filecoin itself. So we want to make it really easy by providing the right set of syscalls and so on. We'll be adding as well. We're working on user-deployed WASM actors, better customizability. There's some ideas around a new dynamic client that will be using WASM modules for client strategies. Stay tuned for that. And things like, for example, the out-of-the-box membership policies that I talked about, and faster cross-net, subnet calling, and value transfers are things that are on the roadmap. Cool. So with that, I just wanted to leave you with a few resources where you can get started with IPC. So there's, you can go into the doc side. There's also the Mycelium calibration testnet that we've kicked off this week, and Alfonso will go into that later. So yeah, hopefully I got you excited about IPC, the future, the technicals, all the potential, and everything that is in our ambition to make this tech finally the one that delivers scale and great developer performance, great developer experience to Web3. Thank you very much.